My name is Skyland Purdy.
So when creating our simulation, what we wanted to do is create an accurate flight model that we can look back at when building our actual rocket that reached transonic speeds and stayed under the ceiling height of 13,000 feet. So what we wanted to get out of this, creating the simulation, is a better understanding of the physics of flight and to learn from the critiques of the NASA experts, and again, develop a successful simulation. Some assumptions we made were an initial altitude of 330 meters at Jacksboro, which will be our launch site. Our wet mass is 6.5 kilograms, and we assumed a drag coefficient of 0.23, and we also assumed non-constant thrust from a graph we found online, and changing air density and speed of sound also from a table we found online, and also we have a one-dimensional simulation.
Okay, so the engine that we chose for the sake of the simulation was the L610 FX, and that engine had a wet mass of 3.7 kilograms and a dry mass of 1.6 kilograms. Using that, we used the burn time and also the difference between wet mass and dry mass to calculate the mass flow rate, assuming that that was constant throughout the thing, even though we understand it's not, simply because we could not find an actual mass flow rate online for this given engine. And then, like mentioned earlier, we did use this online thrust curve from thrustcurve.org, and we will explain later how we use this thrust curve to interpolate our own points.
Did you check on the availability of that motor?
So while we know that the FX is not being widely produced anymore, we checked and we can still access one.
Really? Wow, good for you.
So different elements that kind of went into the design of this rocket. So we had a diameter of 5.5 inches, and then we decided to use the ogive nose cone for the sake of the fact that the ogive nose cone provided us the lowest coefficient of drag and would thus impair the flight of our rocket the least. And the reason why our diameter is so large is because when looking at the equation for drag, which we have over there, my pointer's not working, love that.
It just probably goes through the screen.
Yeah, that's what I'm seeing. So, but whenever you look at the formula for the force of drag, one thing that we notice is that velocity, any change in velocity would affect the entire equation to a higher degree than any other component, simply because the velocity component is squared in this equation. So as a result, rather than altering the mass, which would change the change in velocity, which would thus alter the equation to a higher degree, we instead opted to change the cross-sectional area of the rocket. So by doing that, we decided to change the diameter, and we saw that that allowed us to remain under the ceiling height while also still reaching Mach 1 speeds.
This is one of our free body diagrams up on the launch pad. The bottom arrow here is gravity pushing the rocket down, and the up arrow is the launch pad pushing back, according to Newton's law. And here we have the drag going down, because as the rocket goes up, the air gets compressed and pushes down against the rocket, and the thrust arrow is going up. And this is the burnout, where the engine stops thrusting and there's no longer anything else pushing the rocket up, and there's only drag and gravity pushing it back down. And at apogee, there's nothing but the gravity affecting the rocket. And during descent, gravity is going down and drag is going up as the rocket is going down. And at landing, gravity and the net force are equal.
Okay, so looking at the graphs for our simulation right here, first we showed the altitude and kind of just emphasizing that we are remaining under that stipulated ceiling height right there. And our apogee is, around 200 meters below that ceiling height, so we still have a whole bunch of room should we decide to alter motors or change any aspect of our design in order to increase the margin of error that we have for Mach 1 speeds.
Nice chart, by the way.
Thank you. And then this is just the formula that we used for calculating altitude. Again, emphasizing that we used integration in order to derive this formula from the velocity formula. And then these are two graphs for velocity. The one on the left is in Mach numbers, whereas the one on the right is in meters per second. The one on the left, again, emphasizes that the second aspect of the parameters that were set for us, which were to surpass Mach 1 speeds, and this graph shows us that we are indeed breaking the sound barrier, going about Mach 1.08. And at the top we can see that that's the moment at which we experience maximum drag because, again, velocity and drag are inversely proportional to each other. So you experience the max drag as velocity reaches its maximum point. And then we can reach an inflection point right here, which we can see emphasizes that is the point of minimum acceleration. And that also shows us that's the time of burnout. And then the rocket begins to transition into its coasting ascent until we get right there where the velocity equals 0, emphasizing that that is the point at which we reach apogee. And then moving over to the left graph, the reason why we included this one is to show that after we drop below apogee and deploy our parachute, we start to try to enter our terminal, or we try to enter a point in which we try to find our terminal velocity. But as was stated earlier, there isn't an absolute terminal velocity because air density continues to change. So that second graph is emphasizing that there is in fact a curve because air density continues to change throughout this entire time. So the rocket continues to try to find its new terminal velocity, which is a point that it can never actually reach because it has to continue following this curve. And that is the formula that we use for velocity, which we integrated from the acceleration formula. And so this is our acceleration graph. Again, you can see over there, the point that I've circled for maximum thrust, that is one of our local maxima right there. And that's just again emphasizing that acceleration and force are directly proportional to each other. So as force increases, acceleration would increase, and so that is again shown through that local maxima. And then after we reach our point of maximum thrust, the thrust starts to peter out until we eventually get to our lowest point of acceleration, which is our greatest point of negative acceleration, which would also be the time of burnout, 5.6 seconds after we initially launched the rocket. After time of burnout, the acceleration continues to try and reach negative 9.8 as the rocket enters its coasting ascent up until the point at 23.6 seconds that the rocket eventually reaches its apogee. I think it's also worth noting that at the point that it reaches apogee, the acceleration is equal to the initial acceleration right here, which is negative 9.8. After that point, the parachute is deployed and the rocket begins its descent downward. And that is the formula that we use for acceleration.
Oh, you got a question behind you.
Why does it cause that W right near the beginning?
So that is the thrust curve, and you'll see that whenever we pull up the thrust curve that we got from online. But the thrust isn't constant throughout the entire thing, and it actually doesn't reach its point of, it doesn't actually reach the point of maximum thrust until about 2.3 seconds after we initially start releasing propellant. So it kind of goes through this, W effect that you're saying. And this is our thrust curve. As you can see, it does dip down before it again shoots back up. The other graph was just compressed, so you couldn't see all those individual divots. In this one, we did choose to expand it and create a smaller viewing window so that way you could see, more of the points. This was the curve that we found online from thrustcurve.org. And as was mentioned earlier by previous groups, they struggled with, using these kind of very sporadic, spread out time intervals. So in order to accommodate for that, we calculated the instantaneous points of thrust at each of those individual points in between, and using such linearization, we produced our own thrust curve at time intervals of tenths of seconds. So every 0.1 seconds, we have our own data point over there, and it closely matches this one over here. And for this one, this equation over here, or for that graph over there with the thrust curve, we can again see that the point of maximum thrust is also the point of maximum acceleration, or one of the points of max acceleration, which we saw in the other graph, before the thrust again begins to peter out until the point that you get zero thrust, and that also emphasizes the point of the greatest negative acceleration, or for this case, the point at which the acceleration dips to the lowest point on the graph. After that point, we've used all propellant, so thrust for the rest of the flight of the rocket would be 0.
So the outcomes that we had some challenges, which were, again, circular references, and we had to learn how to avoid those. We had a limited timeline, so we weren't able to fully do all the things we wanted to when we would be building our full rocket, and then also staying under the ceiling height. But we did end up building a successful simulation.
And so one thing that we saw through our simulation is that it was hard to calculate this, but we do recognize that the coefficient of drag does continue to change after you reach that area of supersonic, transonic speeds. So that was not accounted for in this simulation, but we would like to hopefully account for that in the future simulations or future iterations of this model, so that way we can create a more accurate simulation of the path of our rocket. And then we also noticed there were inconsistencies with the burn time and the thrust, simply between the different sources, whether that be thrustcurve.org or the hypertext catalog for the actual burn time of the engine, simply because it shows like an average burn time, and it's hard to account for that entire range in Excel. And then also the fact that this is just a one-dimensional model, so we don't have 3 dimensions or 2 dimensions when accounting for the simulation. And these are the sources we used in which we found out the thrust curve, the table that listed the different speed of sounds at various altitudes, the variable air densities across those different elevations, and also the coefficient of drag for both our parachute and for our given nose cone. Yes?
You might have mentioned this earlier, but what was your coefficient of drag and how did you all arrive at that?
So,
0.23.
yeah, I believe it was 0.23. And we arrived at. Over here? Yeah, 0.3. So we arrived at that number by looking up the coefficient of drag for a given nose cone, which was the OGA's nose cone. So just based on the geometry of the specific nose cone that we chose, that's how we reached that number.
Probably from an average perspective, it's going to be low because you're going to hit a ramp up hypersonic. But, PDR, you'll have CD versus Mach and anyway, yeah, look really good. Great plots, good presentation. Any other questions for him?